Hello everyone. In this video, I'm going to show you how to work through the NREL SAM or System Advisor model. This should help you kind of go through the exercise. So when you launch SAM, this is the welcome page. From here, you can follow the worksheet or the assignment, go through the step-by-steps here. I'm basically going to go through this in a video here, so this should help you get through it. I'm going to start a new project. Click on New Start a New Project. Okay, and the SAM tool allows us to analyze, basically run different scenarios of different energy systems. What's really special or unique about SAM is that it gives you basically a real time, or it gives you the cash flow, really the financial implications for a project across a long horizon, 25, 30 years down the road. It gives you the yearly cash flow, it gives you the production, annual production. It also utilizes other tools that NREL has built, like the PV Watt tool, which allows users to estimate the performance of solar systems across the US and abroad. So these are very good tools out there that have been built by the National Renewable Energy Laboratory, basically funded by the US government. And these are free tools out there that you can use to make better decisions in terms of, if you want to do a renewable energy project, what that would look like. And so I'm going to do one on wind since that's the latest topic we looked at. And that's also an assignment. So I'm going to click on wind here. Okay, there are different options here. I'm going to just look at so you can actually look at a no financial model. You just look at the LCO calculator, etc. I'm going to look at it. Let's run a scenario. Let's say, we have one owner, a single owner, and they decide to develop a wind farm. Okay, so I'm going to keep power purchase agreement, single owner. Let's say okay, and the log box should pop up. In my let's see here, I want to make sure I follow the default case here step by step, so you won't have any trouble when you do this on your own. I'm gonna click on, and you can pick different regions here. And this is a great, so there's different representation of typical wind resource, wind profiles, depending on where you are in the country. So we could pick California, etc. I'm going to pick Texas here, Texas, Northwestern Texas. Aside from this assignment, you can try out different locations and see what the effects are as well. That'll be on your own if you wanted to try that out. So I'm going to click on the Northwestern Texas Flatlands, and then I'm going to go into wind turbine, where I'm going to choose a type of turbine. I'm going to use a 3 megawatts turbine. So I'm going to scroll down to threes here. And let me specifically pick the Siemens one here. The Siemens SWT 3 megawatt 101 meters. So this is the first part. The first part of your assignment was estimating the LCE, levelized cost of energy, with a 3 megawatt turbine, and the diameter was approximately 100 meters, right? So this is very close. So I'm going to pick this one. Then I'm going to pick the wind farm here. Okay, so in our scenario, we had 130 wind turbines, and they were laid out in a 10D by 5D configuration. So I'm going to just leave everything blank here. And what's nice here is you can actually pick one turbine and see what it looks like. You could pick a desired farm size and then decide how you're going to lay it out. I'm just going to do the number of turbines here. You can kind of estimate what the size of this afterwards if you wanted to. Turbines per row, I'm just going to put 13. And then number of rows 10 to make it easier. So 13 by 10, that's a total of 130 turbines. That should be the number of turbines I wanted in the initial system. So 130 turbines. I'm going to lay this out. I can do no offsets if I want. Just to, I'm going to set it up so that there is an offset. So you can kind of see maybe that would be beneficial or not. So turbine spacing, this is basically the 10 diameters. Okay, so I'm going to put 10 here. And then I'm going to set this to 5, the row spacing. And and I'm going to offset it by 5 as well. So you can kind of see what the offset does. I mean, you could do this or not, but for now, I'm just going to lay it this way. You don't really have to, okay, if you don't want to, and see what happens here. There may be some small differences on the total megawatt hours of production you see. Let me just set it at 5, so I can put an offset here. You kind of tell, like, this dimension here, that distance, it's about 1,000 there. Okay, so 10 times the diameter. Diameter is diameter of a turbine here is 100 meters. So 10 times is about 1,000 meters. So you see this 10 diameters. And this distance here should be 5 diameters, right? So about 500. And you can tell like 500, 4 tons. So you can tell the distance between these turbines. Okay. So, and you can play around, you can change it. You can do like different each row, every hour, offset type, etc. Um, it really depends, but I mean, for now, we're just hypothetical, so we're just gonna leave it as is. Now let me go to the next section. I'm gonna keep the losses untouched. Let me go to the installation cost. So you guys can specify some of these in more detail. I'm gonna make it very simple. I'm gonna keep everything zero except for the turbine cost. I'm gonna set this value at 1500. Okay, then I'll set everything else to zero. Okay, just for simplicity. Okay. And I'm gonna leave everything at the default value. Okay. And then I'm gonna go to the operating cost. So there's a fixed operation means right now it's set at $43 per kilowatt year. I'm gonna change that value to 70 here. Okay, is that just like in our first problem? And now I'm gonna move on to financial parameters. This is where we gotta account for that capital charge factor. Okay. Now this real discount rate is not gonna be the exact value, so I'm gonna just change it to roughly 12%. Okay. This is going to roughly match what we were doing in problem one. There are some other things here that, we can't really specify because, we leave it on our analysis, like the Fed income tax rate, etc. Try to keep everything in default values here. Okay. Now I'm going to move on to the federal tax credits or, sorry, incentives. Right now, by default, there's this federal production tax credit. I'm going to zero that out for now because I'm going to assume there is no incentive. Okay. And then everything else, I'm going to leave it as default values. And then now I'm going to let's press simulate here. Okay, so I think the double check, everything looks good. Okay, I'm going to press simulate. Okay, it's going to simulate. Then you might get a message saying it's negative MPV, which is okay. Say okay. And then we get a summary of our output. Your tool may be a little bit sluggish here. If you try to drag it down a lot, just be patient. This will respond. This is a summary output here. It tells you the LCOE of your system. You probably got a similar number. If you look at the nominal value here, you probably got a similar value when you did your analysis on your own. So you won't be exact, but if it's similar, it's okay. The capacity factor is probably very similar to what was given in the original scenario. The total energy production for this plant is given by this top number here, basically 1.3 billion kilowatt hours, or another thing about it is 1.3 million megawatt hours, right? So roughly that. It tells you the internal rate of, so this project, if you look at the NPV, net present value, it never reaches positive NPV. So you never recover that initial investment. So probably, it's not an attractive investment. We could probably figure out why, but we talked about this before. And this tool gives you a lot of information, right? It gives you the generation. It actually goes even more depth. You can look at the data tables, and you can look at the daily power generation, the system power generated per day by hour. You can even look at the wind data, etc. Look at the cash flow data. Look at profiles, different profiles of the energy. So you can look at system power, wind speed throughout the month here. Okay. Let's look at the heat map. This is again when you had the most generation. You can tell early in the morning or late at night. During the middle of the day, don't get as much. That's what this shows. Let's get the PDF and CDF. So some of you probably, or maybe some of you all can read this very well already. Some of you may not. So the PDF or this PDF/CDF stands for probability density function / cumulative distribution function. So basically the area under the curve is going to equal to 1 here, right? For the, basically, if you look at the left axis, that's the PDF. If you look at the right axis, y-axis, y-axis, that's the CDF. So it asymptotically should reach 1 or 100%. This blue dashed line here, this is basically the 50% mark, right? So if you look at here on the right hand side, 50%. Okay, so this is basically your mean, right? So on average, our system is generating 130,000, or system power generated is 130,000 kilowatts, or 130 megawatts. Okay. So the way these are, sometimes we have no wind, so we have highest percentage when there's no generation, and then there are some times that we get very high generation, right? So the maximum power generated that we see is 320 megawatts here. Okay. We can also do things like the wind speed. So here it's a little bit hard to see, but the fact that you have so you can tell by the CDF, you see how the asymptotic reaches 100%. The fact that there's a 24 here means that the maximum wind speed in this data is 24. Okay, but most of the wind varies around, it's within this range. So again, this blue dashed line means 50%, right? So this is a mean. Okay, so the CDF tells me basically the probability that your x-axis value is less than that value. So every value is less than 24, 100%, right? So, and then 50%, probably that the wind is under, I would say that's about 8.6 or 8.7 is 50%, right? Because this is basically at the 50% CDF value. Okay, so this is a great tool, and hopefully through this assignment you get to play around with this, and you get to kind of run different scenarios. This is a very very popular tool, and hopefully disclose you to some of the ways that we kind of do sensitive analysis if you're trying to design a system. What are the impacts of more incentives? What's the impacts of greater generation? What are the impacts of higher efficiency, etc. You can test all of these things out using a tool like this. Okay. Hopefully this helps. If you have any questions, feel free to reach out to me. Take care. Bye bye.